In this video, we're going to talk about the overall structure of the atom. We're going to go briefly over the two regions of the atom, the different subatomic particles that exist in the atom, some properties of those subatomic particles, and we'll also get into how to determine how many of each particle a specific atom will have. All right, so the objectives overall is I'm going to do a very brief history of the atomic model. And then again, we're going to talk about the two regions and the three subatomic particles, figure out how many, and then we're also going to talk about what ions and isotopes are and how those affect the numbers of each of the three different particles. So if you are ready, let's start. So in science, a model is just some representation of an idea or a concept. Now, this representation can be a picture, it can be an explanation, it can be some equations, it can be any combination of them. The key thing about a model is that it's consistent with what we know and what we can observe, and that it can change, right? So it can also offer a little bit of predictive power as well, at least if the model is good. Last year in bio, you guys learned about model of the cell, what the cell looks like, the different parts. It was an oversimplified representation, but it got the point across and you could start making some predictions with it. Now, one key thing about scientific models is that scientific models will change as our evidence gets better and better. Right? This is not a bug of science, this is a feature. If you've been following in the news, you have doubtlessly seen some stories where people start complaining about science's inability to predict something that happened and how the model was wrong, so scientists are wrong and science is bad. No, it's just that we didn't have a lot of information to work off of. And now that our information is getting better and better and better, our models are becoming more and more and more accurate. Now, if we talk about the atom, there are three models of the atom I want to briefly go over. I'm not going to get into much depth on these, but we'll start off with the original scientific model of the atom, which is called the billiard ball model. This was from John Dalton in the early 1800s. Dalton was a naturalist, which is an early form of a scientist, and he determined his atomic theory based on the very crude measurements that he was able to take at the time. The reason why his model is called a billiard ball is because he thought atoms were just spheres. They couldn't be subdivided into smaller pieces, they didn't have any overall charges. Each atom was just a different type of sphere, like a different type of marble. And when they reacted, they just combined in different ratios to form new products. And atoms of one element were different than atoms of another element, just like a marble of one type is different from a marble of another type. About 110 years or so of active development and increasing our knowledge got us to the model that you guys are familiar with, the one that you've been using in biology last year, which is called the Bohr model. Right? In the center of the atom, you have the nucleus, and around that, you have the electrons, and the electrons sit in these rings that keep going as you go outside. The first ring holds 2 electrons, then 8, and so on and so forth. So this is the Bohr model. It's named after physicist Niels Bohr. And for the vast majority of what we're going to do in this class, the Bohr model is perfectly acceptable. Right? It gives good enough predictive power and it's relatively easy enough to understand for it to become fairly useful for you guys. But it's not the current model. The current understanding of the model that we have is called the electron cloud model, also known as the quantum mechanical model. This model is based off of probability. So you still have the nucleus in the center, and that nucleus contains the protons, the neutrons, and outside of that, the electrons exist in this cloud. We don't know exactly where they are in the cloud, but we have a reasonably high probability of finding them in a given location. Now, just to give you a little bit of a heads up about some of the atomic structure, right? There are two overall regions for the atom. The first region is the nucleus. The nucleus is the small, really dense portion of the atom that's in the center. The reason why it's dense is because the nucleus contains almost all of the mass of the atom. Right? That's because it has the protons and neutrons, which are the two things that have mass. Outside of the nucleus, we have the electron cloud. The electron cloud is extremely diffuse. All of the electrons the atom has will be somewhere in that cloud. Now, the electron cloud, so electrons themselves have essentially no mass, but the size of the cloud itself is about 100,000 times bigger than that of the nucleus. The nucleus is tiny. We're talking the nucleus is like billionths of a meter. If you want a good approximation to kind of get the scale of how large these things are, if we assume that the entire atom itself is, say, the size of Gillette Stadium in Foxborough, then the nucleus is going to be the pit of a cherry placed on the 50-yard line. That's about the size differential we're looking at. However, the pit of that cherry would contain all of the mass of the entire stadium. Now, the three particles, again, we have protons, we have neutrons, we have electrons. The protons and neutrons exist in the nucleus. Protons are positively charged. Neutrons have no charge, they're neutral. They both have a mass, and AMU is just a made-up number that we have to make our life a little bit easier. Proton is defined to have a mass of 1 AMU. The neutron is a tiny, tiny bit heavier, and I'll get into why that is in a second. The electrons, which are in the electron cloud, have a negative charge, and their mass is essentially nothing. Now, it isn't exactly nothing. Again, matter has to have a mass, that's by definition. But the mass of an electron is like 2,000 times smaller than the mass of a proton. So, for the amount of electrons an atom actually has, it really doesn't affect the mass at all. Right? So we'll just assume it's 0 to make our life easy. Now, the reason why I said a neutron was a tiny bit heavier than a proton is because a neutron, the easiest way to think about it, is that a neutron is kind of like a proton and an electron jammed together. So you still have that tiny little mass from the electron, making it a little bit heavier. Right? So those are the three particles, those are the two regions. Now, I do apologize for this incoming wall of text. Right? But we do have to go over some vocab before I get into actually being able to count those things. So some definitions. The atomic number is simply the number of protons an atom has. Right? So if we look at a carbon atom, carbon has an atomic number of 6, meaning that it has 6 protons. The mass number is the total number of protons and neutrons in the atom. Right? Since those are the two things with mass, the sum of those is the mass number. Now, point of order. Okay, I apologize for the wall of text that's about to be incoming, but there is some vocab that we have to go over first. Right, so the first piece of vocab is what's called the atomic number. The atomic number is simply the number of protons that an atom will have. So if we look at carbon, carbon has an atomic number of 6, meaning that there are 6 protons in the nucleus. Every carbon atom, no matter where you are, is going to have 6 protons. If it has a different number of protons, it's a different element. The second number is called the mass number. The mass number is the sum of everything in the atom that has mass, which are the protons and the neutrons. So you add them together, you get the mass number. If we look, for example, at carbon, 12, so carbon with a mass number of 12 has 6 protons and 6 neutrons. 6 plus 6 give us the 12. Now, one thing I should point out about mass number, which is really important. Mass number is not the decimal number that you see on the periodic table. The number on the periodic table is average atomic mass. Right? The average atomic mass we'll get into probably a little bit later, but it's the weighted average of every carbon atom in existence. Right? So it's the weighted average of the mass numbers for every single carbon atom out there. Isotopes are atoms of the same element, so they have the same number of protons, but they have different numbers of neutrons. That means they have different mass numbers. Right? So for carbon, for example, carbon has 3 isotopes. Carbon 12 with 6 neutrons, carbon 13 with 7 neutrons, and a very rare radioactive form of carbon called carbon 14 with 8 neutrons. And carbon 14 is actually what they use in radioactive dating. Right, so all 3 of them are carbon because all 3 of them have 6 protons, but they have different numbers of neutrons and different mass numbers. And again, if you take the weighted average of all of those isotopes, based on how many of each there are, that will get you the decimal number on the periodic table. We also have what are called ions. Ions are charged atoms. The way that an atom becomes charged is either by gaining extra electrons or losing electrons that it already has. Positively charged ions have lost electrons. Remember, electrons are negative. So if I take away negative charges, it becomes positive. So less electrons is positive, more electrons is negative. Now, the way that you'll see this written is you'll see this written as what's called a nuclear symbol. So I have this nuclear symbol or nuclear notation right here for a certain type of magnesium. The symbol of the element always goes in the center. And notice for the elements, the first letter of every symbol is capitalized. The second letter of every symbol, if it exists, is always lowercase. The atomic number or number of protons is in the lower left-hand corner. I don't have to give you that number, right? If I say magnesium, you can just look up on the periodic table that magnesium has an atomic number of 12. So I can give it to you, although I don't have to. Above that is the mass number. The mass number, again, the number of protons plus neutrons. And in the upper right-hand corner, you have the charge. The charge is just the difference between the number of protons and electrons, right? So if I wanted to solve for this right here, right, so my number of protons is the atomic number, which in this case is 12, right? Atomic number 12. Number of neutrons is the mass number minus the atomic number, or in this case, I'll just do it over here, minus 24 minus 12 is 12. So we also have 12 neutrons. Electrons is atomic number minus charge. So 12 is my atomic number, minus 2 for the charge means I have 10 electrons. Now please note, if the charge is negative, you'll be subtracting a negative, which is adding. Right, so this is figuring out how many protons, neutrons, and electrons something has. This is a task I'm going to ask you guys to do and you'll be graded on. Now I'm going to let you guys practice on a few of these. Right, so I have 3 of these coming up. Let's practice. So the first one is going to be bromide Br- with a mass of 81. The second one will be Einsteinium with a mass of 255. And the third one will be technetium with a 2+ charge and a mass of 99. Pause the video, take a few minutes, try to figure out how many protons, neutrons, and electrons each of these have, go back to the previous slide if you need help in figuring it out, and then pick it back up once you think you have a solution. Okay, so we have protons, neutrons, electrons. For bromide, atomic number 35, so 35 protons. I'll do electrons next because that's easy. 35. Now, you see a minus here? That minus means -1. Again, chemists are lazy. We try to avoid writing the number 1 whenever possible. So 35 minus -1 or 35 plus 1 means we have 36 electrons. And then for neutrons, I just do 81 minus 35, right? So 81 minus 5 is 76. 76 minus 30 is 46. So we have 46 neutrons. Right, so that's bromide. Einsteinium again. Proton, neutron, electron. Protons, we have 99. Electrons, there's no charge in the upper right-hand corner, so those numbers are the same. 99. Neutrons is 255 minus 99, so that's going to be 156. And then technetium, again, we'll do our protons, neutrons, and electrons for that. Protons, technetium has 43. Electrons, 43 minus 2, so that will be 41. And then neutrons is 99 minus 43, or 56. Right, so that's protons, neutrons, and electrons. And that's the video on this, so if you have any questions, please feel free to drop me a line. Otherwise, I'll see you guys in class.